Continuing on with molecular mechanics energy terms, we have the angle bend terms. We have that the energy of angles is equal to the sum over all of the bond angles in your system of Ka, the bond spring constant, times theta, the bond angle, minus theta eq, the equilibrium bond angle squared. So this term is very similar to the term for bond lengths in that it is basically exactly the same. So we have, in terms of parameters, for our bonds we have theta eq, sometimes theta not, but theta eq. I'll use the same terminology to be consistent, is the equilibrium bond angle, equilibrium bond angle, and that would be in units of either degrees or radians, but more typically degrees in terms of what you see tables of parameters being. Maybe it's stored internally in radians to make it more easily for the code to work with, but typically when we see it, we're looking in terms of degrees. We also have Ka, or perhaps K theta, which would be the angle spring constant or force constant. And that would be in kcal per mole. And typically this one is expressed in kcal per mole per radian squared. So typically you would have theta in radians, or theta in degrees minus theta eq in degrees gives you degrees, square that, and then convert that to radians. And then you'd have kcal per mole per radian squared times radian squared gives you the kilocalories per mole for your total energy, and summing over all of the angles as well. The variable of interest is, of course, theta, which is our bond angle, typically expressed in degrees, but again, be careful of this caveat of whether it's in degrees or radians. That's sometimes a landmine that you have to navigate your way around. Okay, so then plotting out this function, how does this look compared to what the exact function would look like if we did it with some very high accuracy quantum mechanical method? Okay, so we have, as we saw, theta eq, our equilibrium bond angle, versus theta. Theta can be in the range of 0 to 180. So unlike bond lengths, which go from 0 to infinity, they are unbounded on one side. Bond angles are bounded on both sides in terms of that limitation. So the exact would go up to some very, very, very large energy as you go towards 0 degrees, and it would approach towards some finite energy at 180 degrees. For molecular mechanics, this function is a parabola that goes up, up, up. When it reaches 180 degrees, it starts going back down on the other side as you get to bond angles which start decreasing on the other side. But overall, the same general functional form as what we saw for bonds. So you have the same kind of origin where you can take a second order Taylor series around the minimum and you can derive out what the parameters are, where your equilibrium bond or your spring constant is 1/2 the second derivative evaluated at the equilibrium bond angle. All right, so we have one particular caveat there, is that as you go over 180 degrees, the potential actually should go to a first derivative of 0, and in molecular mechanics it doesn't do that, but that's an issue for another day when we get into molecular dynamics. Okay, so we have the same origins as bonds in the fact that this potential energy function is convenient. Yeah, it's very easy to derive. It's very easy to get for pretty much any bond angle you're interested in any system. It's easy to compute. There's just algebra. Subtract this, square it, multiply it, sum over all the things. And then you have, it's also quite quick in that doing a single subtraction, multiplication, and then sum is all pretty quick mathematical operations to perform. If you wanted to get a function that actually looked like this and had all the right asymptotic behavior, it would be a sum of two cosines. And cosines take a lot more computational effort than just simple mathematical operations like addition and multiplication. Okay, so then the other thing we need to do is specify all of the angles in our system. So that would again be either handled by the internal program, or if you were doing it manually, you would have to look at the system. So for water, we have one bond angle, two adjacent bonds, one bond angle. And then we have for something like ethylene, 1, 2, 3, 4, 5, 6 total bonds there. And for something like methane, it gets very complicated to draw in 2 dimensions, but there are in fact 6 of them. It's all HCH pairs. So you have 1, 2, 3, 4, and then the ones that go across from each other, 5 and 6. Okay, so this energy function that I plotted here, this would be the energy you would get if you were keeping all of the other factors of the molecule the same. So for example, if we had water, we'd be looking at keeping the bond distances the same and just varying the bond angle. So that'd be some kind of trajectory like this, where I've got the bond angles are changing, but as I saw, the bond lengths are staying the same, so I'm not getting that quadratic penalty from varying the bond lengths as I go about that. Okay, so that is the angle bend term, second term out of our bonded terms in molecular mechanics in force field energy functions.